This is still 1.9. And the way that I want you guys to approach working with graphs of inverse functions is I want you guys to think of it as something very, very easy. This first statement here, if you read it through, is kind of annoying, much like most of the way they define things in math textbooks. What I want you guys to think about is if you have a graph of an inverse function, a couple of things happen. If a point, and this is where I wanted to break it down into, if a point AB is on f of x, this is what the whole idea of graphing with inverses. Then points.
What is on f of x? Like the whole graph?
If this ordered pair is on f of x, if some ordered pair, whatever it is on that function,
okay.
then the point BA is on the inverse of the function. That's really all it is. So if you have an ordered pair, if 1, 2 is on a function, if that function has an inverse, then 2, 1 is on the inverse function. That's all that is.
So how would you graph it?
Not necessarily lines. You might graph lines, you graph curves. So what I'm going to try and get you guys in the habit of doing here is, as we get into some of the functions and graphing them, the regular function, you'll get the regular function, find its inverse, and then we're going to plot points and make it really easy to work through, okay, to verify how these things work. Yeah, the f prime of x means inverse. So it works out to be really kind of basic, to be honest with you. So if I want to look at an example, let's see, I think I had it here. A really easy example. I have a function, f of x is 2x minus 3, and then the inverse of the function, I already wrote it out as f prime of x is 1/2 times the quantity x plus 3.
Same thing as x plus 3 here.
Yes, sir. Exact same thing. What's that? Yeah, because remember when you did exponent rules? A to the negative n was 1 over x to the n. That's the same. Anything to the negative 1 is 1 over x. It's inverse. That's all that is. So what we have here is just two graphs. And I'm going to kind of just throw them on I'll get you guys some graph paper here in a second. We might even have some still lying around. And I'm going to show you how this stuff works. Okay? Grab 2, because you'll need 1 for tonight. Thanks, Julie. There wasn't any choice then. So, there are only two shipwrecked people who reach across each other. Right there? Okay. So let's plot this. 2x minus 3, slope-intercept form, really, really easy to work with. Start at negative 3. Walk your slope in 2. Okay? It's slope-intercept form.
I don't like these graphs because you can't like see the baseline. Yeah, no, I was helpful place. Yeah, I have to draw them in.
I just did the first one.
Oh, the 2x and half, so
Yeah.
maybe the 1/2.
Yeah.
The 1/2 would be.
Oh, I don't like these graphs because, you know,
So now on the other one, remember this is also the same thing as 1/2 x plus 3/2. Right? 3/2 is how much?
oh, and this one.
1.5. Is that okay to graph 1.5 without being too annoyed by it? So if I start at 1.5, I go up 1 over 2, up 1 over 2, up 1 over 2, 1 over 2. Now, it's going to be tough to tell from just the graphs until we pick out ordered pairs. How did I figure what out? I distributed the 1/2 and wrote the slope intercept form of the graph. Okay. What happens here is that if functions are inverses of one another, they're always going to be reflected over the equation y equals x. Always, always, always. The function y equals x is this. Okay? Intercept of 0, slope of 1. Therefore, each point is reflected over that. So if we start to think about something that's very, very easy to work with, for example, if I used 3 for x, if I use 3 for x in my first function, what's my y value? 3. So my ordered pair here was, well, that was kind of a dumb luck guess. Okay, bad example. Because what's the ordered pair for the other one? 3 and 3. I just didn't mean to do it that way, but it worked. Sorry. That was kind of dumb luck. So if I did, I'm not lying, guys. I just guessed on 3. I had no idea. Wasn't paying attention.
You always want us to put f of x equals x too.
Oh, that y equals x? Yeah, I'd like you to do that because that way it will help you to see that it works, or if it doesn't work. Let's pick a different pair. Let's try it at 5. I just chose, to be honest, the reason why I picked 3 is because I went to this and I was looking to see what could I take half of that I knew was going to work. I was picking an odd. That's the only reason I picked 3. I did not even look at the graph and notice that that's where they intersected. It just happened to be dumb luck. So let's pick 5. Okay? So if I pick 5 for x, so if I use 5, 7 for the 1 on that side, what should the ordered pair be on the other side? 7, 5. So let's check that. Does 7 work? If I use 7 over here, half of 7.
Wait, so you don't need to use the same x for both sides?
No, because what happens here, in order for them to be inverses one another, AB here should be BA there. So if I do half of 7 plus 3, well, what's half of 7 plus 3? So the ordered pair flips.
Yay.
That's what we're looking at here. At 5, it was at 7, which means here at 7, it's 5. That's all that means. It's reflected over the line y equals x. And the reason it's y equals x, because f of g of x is x, and g of f of x is x. That's where this all comes from. I'm just picking ones that I know that will land on there. So if I'm picking, The reason that I picked odd numbers is because I was taking something here that would be half. It'd be easy. It's just easier to work with. That's all. When you work with these things and you're doing the graphing to verify it out with the ordered pairs, you'll know what numbers to pick. Yes, ma'am.
What's the point of the line in the middle?
That just means it's reflected over that line.
Okay.
That's all that means.
Okay.
It's just been flipped over that line. This curve has been, or not curve, this line has been flipped over that axis. It's not like, you don't want to think of it as, you're looking for that line of symmetry of, there are certain things that get you to that to make it work, but for here, we're talking just pure reflection. That's all it is. I used the original inverse function right here. Remember when I graphed it, I just put it in slope-intercept form just to graph it because it's easier. But then when I was substituting in, I knew that 1/2 times 7 plus 3/2 is the same thing as half of 7 plus 3. It was just easier to do it, that's all. It's the only reason why I chose to use that. Because this ordered pair on one function should be flipped if it's an inverse on this side. Because if you have the ordered pair AB for one of them, the inverse should be BA. That's all I was doing. And again, the reason why I picked those odd numbers is because I knew it would work better with the halvesies. That's all. It's
How does an odd number
when you add two odd numbers together, you get an even number.
Right.
That's why I picked the odd number.
Okay.
That's all. It's the
But
only.
if we take half of odd numbers,
You're missing because if you pick 5 for x, what's 5 plus 3?
oh, you do the duh.
Wait, did you say if you add two odd numbers equal? What's 7 plus 5?
Whoa.
Oh. I thought it was 13.
Oh,
Yeah!
That's almost as bad.
Thank you for everybody with the quick little 12.
That was, Mr. That's almost as bad as my no one knows what half of 43
Oh, that was
is.
great. No one knows what half of 43 is.
And of course it was Cullen who said the answer too.
That was awesome. Let's do another one.
Good job.
This is going to mirror the idea of what the homework is going to look like tonight. Actually, I'll just throw it. I put this one in here. In the homework tonight, you're going to have a question that looks like this. Find the inverse of the function, graph both the regular function and its inverse.
Dang.
Describe the relationship of the graphs of f and f prime. Basically, it's reflected over y equals x, like all of them. And then, what's the domain? And it's really very easy. Here's the thing, though. I'm giving you one of the problems that is of the more difficult variety because you are graphing a rational expression. If you remember that from last year in Algebra 2, it was section 9.3, because I know you guys memorize all the section numbers because that's what you do. And if you recall, you had all of these rules about graphing that you probably forgot, about asymptotes and things like that.
I forgot about those.
Well, it's a good thing that I'm a nice person sometimes, and I've made a copy of the rules.
Sometimes you right there.
Exactly. And I'm okay with that.
Except you need 2 million copies. What do you do?
I feel like stabilizer or no?
No.
Sure. I think you did last year. Okay. So what happens here is this is going to be kind of the rules for some of the graphing, and we'll get to that here in a second. The tricky part of this problem is finding its inverse. Okay. The tricky part's going to be finding the inverse. So if our original function is x plus 1 over x minus 2, the inverse of the function, well, in order to solve that, I have to change, let's do it this way, x and y. But now how many y's do I have to put in there? I put it in twice. So the inverse of this is going to wind up being, let me write this out. The inverse will be switching x and y again. And now you have to resolve for y. And this is where it can get kind of messy if you're not careful with your algebra. And that's why I wanted to use a problem like this today. Because the other inverses are very similar to what we did on Friday, a little bit of what we did yesterday. They're not difficult. Yep, we're going to multiply both sides by y minus 2. Okay. Now I'm going to distribute the value of x. So I have xy minus 2x equals y plus 1. Can I get both y's on one side?
Yeah.
How?
You subtract,
You're right.
1 and
Subtract the y and add the 2x to the other side. Watch what happens. If I subtract the y and add 2x, I get xy minus y is 2x plus 1.
then you
Close. What do both those parts have in common on the left-hand side now?
y.
Can I factor that out? Factor out the y then. If I factor out the y here, I get y times x minus 1 is 2x plus 1. Like I said, this is the tricky stuff. What we're doing here is we flip-flopped x and y. I multiplied the denominator to the left-hand side. I distributed the x to both terms to get xy minus 2x. After that, I added the 2x over, and I subtracted the y, which gave me xy minus y is 2x plus 1. On the left-hand side now, since there is both parts of that have a y in common, that's why I'm allowed to factor that y out, so I wind up as a product. And then how do you undo the product? Divide it, exactly. So you wind up with another rational expression. So you wind up with y equals 2x plus 1 over x minus 1. Therefore, that's my inverse.
I thought you were going to do
Hey, can you just go over and show me the original problem? Is it just like x plus 2?
No, it wasn't. It was x plus 1 over y minus 2. Oh, x plus 1 over y, x minus 2. Sorry, I read the wrong line there. So we wound up with, it takes a little bit longer with the rationals to get the inverse. You just have to slowly go through it. When you have the rational stuff like that, you will probably more than often need to factor out some term of a GCF, be able to get it by itself, okay? That's kind of like a little dead giveaway. I know we haven't done one like that. We might have done one last year. I don't remember if we did or not, to be honest with you. But I wanted to make sure I showed you that. Also, show you guys a reminder of how you graph rationals, okay?
Okay,
So-
you have to graph that.
Yeah, that was just the first part. First part was find the inverse. So we have the inverse.
That's a lot. You better have like
Oh, that's why I'm showing you the worst case scenario right now. I think I only have you guys doing like one more of ration. That's it. The other ones are fairly simple. Find that graphic. That's stuff you guys can do. I'm not worried about that. I wanted to spend time with the tough stuff today. So that was our inverse. What was our original function? It was f of x was. Thank you. So now we have to think about how do you graph rational expressions. Rationals, if you recall, have asymptotes. The asymptote, you'll have a vertical asymptote where the denominator is equal to 0. So in my generic function, where's the denominator equal to 0? 2. Okay? So now we're going to look at this thing. This is how we graph polynomial expressions. This is just a polynomials with degrees of 1 is what we're looking at here today. Okay? So that means that our leading term, we're looking at the x-intercepts where it's crossing the x-axis are going to be the zeros of the numerator. That's what that means. So in the numerator of my original function, what's my 0? Original, the numerator. Negative 1. The 0 here is negative 1. So that means there's an x-intercept at negative 1. Yes, sir?
You know how you usually, when we're doing that, when we graph those, when you graph that f of x, each equal to y equals x?
Yeah.
Is there like, is there the same thing when you graph that y equals x, or is that?
What do you mean?
Because isn't that like?
Oh, yes. We'll still graph that y equals x then.
Yeah.
Yeah.
But that's like the original formula for like one of those lines. This is not going to be a line.
No, these are going to be curved. Yeah, exactly.
So is there like a paired for graph that?
For rational?
Yeah.
No.
That's not.
Yeah, no, there's really no parent on that one. It falls into this rule of polynomial. It falls into this generic form. There are I should say that, okay, the generic form of this is the graph of y over x, of 1 over x. If you look at it, because then there's your hooks.
Yeah.
So-
So you would graph that.
Not at all. Yeah, this was the section that we didn't do any parent functions. We went right off of this list and just started putting points in. So we had an x-intercept at negative 1. Yeah, they look kind of cool in the overlap. Asymptote. They had the vertical asymptote at the 0 of the denominator, so that's at 2. Okay. And then the last bit was the graph of f has at most one horizontal asymptote. Now what they're talking about here is if these m and n's. These m and n's are the degrees of the numerator versus the degree of the denominator. The degree of the numerator here is what? It's 1. They're both 1, okay? So that just means that if they're the same, then what do we have? The line, the horizontal asymptote will be the coefficients. What are the two coefficients of x's? 1. So where would my horizontal asymptote be at? 1. I'm going off the 3-step program of graphing for these. The first step was plot the x-intercept. The x-intercept was the 0 of the numerator. The 0 of the numerator was negative 1. Second step was plot the vertical asymptote if there was. It's the 0 of the denominator. In this case, the 0 of the denominator was 2. And then the third step was horizontal asymptote. Well, there's a horizontal asymptote. Since the degrees of both the numerator and the denominator are the same, it's just when you take the coefficients and divide them out, we got 1. Okay? Now from here, that plots you those things. Your graphing calculator at least let you see where the hooks are going. Okay? Now when you did this, you were third quadrant, I think?
Yes.
So you were kind of doing this, you're hugging the asymptote and coming around,
Yes.
and then came through like this. All right. So for all intents and purposes, it kind of looked like that. I do the same thing with the other graph. What I'm doing here is just switching over to my y equals table, or into my hitting the f of x button and going to my graphing calculator on a document.
What are we gonna have to graph?
I haven't decided yet. Probably not. I mean, as in, you'll probably get the calculator because this gets messy. Because you still have to know how to put your asymptotes in and all that. The calculator won't find the asymptote for. I mean, you can kind of guess where they're at, but you still gotta.
Yes, it does.
It throws up the asymptote.
It
Okay. So, oh man, we're running out of time, aren't we? One of the things before we get out of here, let me put this up real quick. The day 2 stuff I want you to do is 40 through 54 evens and then it's the all part stuff. There is only, let's see, on 54, this is where it is. There's only one, that's right, there are two graphs that are rational, like this, that are rationaled up like that. And those will take the longest, that's it. Everything else is really fast to graph through.
Asymptotes always have to be whole numbers.
Not necessarily, they can be fractions. Yeah. The day 3, I might as well put this up if you want to write this down, is going to be 9 through 12, 29 through 32, 69 through 71, 80, and 82. This is all 1.9. This is all in 1.9. I am changing out the problems that we're doing that were already suggested because it's too much variance in the styles to do in one day. That's why I wanted to just go, we did verify yesterday. Today you're creating the inverse and graphing it. Tomorrow we're going to do one-to-one and on-to. Probably a little bit more graphing, to be honest with you. Okay? Yeah, well, obviously don't do the day 3 stuff. These are evens. 40 to 54 is even, so it should only be like 6, it's like 7 problems. But there are only, there's only 2 who want to be rational with the weird graphs. The rest of them are pretty easy. See you guys. Okay.
I don't know how I feel about watching this movie, so.
You'll be okay.